The advances that got us to the point where we can now put a transistor on a computer chip for less money than it costs to print a character in a newspaper, right? The advances that got us there are advances in processing, fabrication and processing over the last 50, 60 years. The advances that will solve the next set of problems related to energy and water are going to be ones that require the design of new materials. You know, Moore's Law was what happens when you have really smart engineers working on a problem of processing and fabrication over 60 years. What has to happen in materials design for energy and water is that we have to invent new materials that don't exist even today, right? We have to figure out the properties we need and then figure out which materials can give us those properties and then make them. And we need to make them in a way that is cheap and scalable. Graphene is a very interesting material that is not new. It's just that we now, since the last 12 years or so, have been able to isolate it. So graphene is actually one of many layers that you'll find in graphite. When you peel one of those layers off, so now you have just one atomically thin layer of carbon, that single layer, which we call graphene, has different properties than graphite. One of the things I'm excited about related to graphene are its mechanical sieving properties. So that is how you could try to push something through it and use it as a filter. If you think about filters, filters are essentially some type of material that has a certain thickness and you're pushing something through and you want something else to come out on the other side, right? You want to remove something from the feedstock. That's what the filter is doing. But what happens is, as you push something through, the stuff you want to get out on the other side has to go through the filter, usually in a sort of diffusive way. That means it's kind of randomly colliding with parts of the filter. That takes energy, right? So that's friction loss, right? So you have a lot of friction involved in these filters, and that means you have to push harder on this end to get stuff to come through. In the area of desalination, what we're pushing through is salt water. And what we want to come out is fresh water. So you want the salt to be blocked. And it turns out that the filter that's been used has been the same material for the last 50 years. It's a polymer. It's called polyamide. And there's been a lot of improvement in desalination over the last 50 years, and the costs and the energy required. But that filter, the material used in that filter, has been the same. What if we rethink the material at play? What if we rethink the active layer material that's separating the salt from the water? Are there new opportunities there? And if you think about that a step further and you think, well, what would the limit of a filter be, right? The limit of a filter would be a single atom thick. Why? Because now, when you push something through it, there's almost no frictional loss. There's almost nothing to go through in the first place, right? So the ultimate filter would be a single atom thick.